This video is divided into three parts. In the first part, I will present an intuition. In the second, we shall mathify that intuition. And lastly, I will leave you with another intuition. Suppose there is a distribution which acts on two random variables x and y. The probability distribution assigns a number to each unique configuration this random variable couple can take. The probability distribution is in some sense filtering these configurations. The size of the hole shown in orange is small as compared to the size of the hole shown in blue. So what our sieve is saying is that the first configuration is 4 times more likely to pass through than our second configuration. Going ahead, we will simplify things a little bit. We are looking here at variables x1 and x2. We know a priori that they both can be either 1 or 0. We can now attach a sieve of our choice to these random variables. The filter or the probability distribution can have any set of values, as long as it follows these three conditions. The total size of the sieve is fixed, that is, it is 1. And none of the sieve holes can exceed the total size of the sieve. And this might seem obvious, but the least size of any hole can be 0 and not less than that. We can use one of the rules, specifically rule number 1, to replace any of these thetas. Like instead of theta 1, we can write 1 minus summation of theta 2, theta 3 and theta 4. We can replace any of these thetas like so. We go ahead by replacing theta 4. Why introduce all these thetas in the first place? I want you to get a better feel for these probability distributions. A set of thetas is one particular sieve. What if we can take a look at all the possible sieves in one picture? I think you might have guessed it already. We can think of theta 1, theta 2 and theta 3 as coordinates in 3D space. This moving red point shows one possible sieve configuration. This tetrahedron is the collection of all the possible distributions which can govern x1 and x2. In other words, each point inside this tetrahedron here is a unique sieve. Now, equipped with all the tools, we are ready to tackle the independence assumption. When we write something like this probability distribution, our hands are forced to observe x1 and x2 together. I like to think about the independence of x1 and x2 in the following manner. If we can observe x1 independent of x2 and vice versa, observe x2 independent of x1, we can assume their independence. If we are observing x1 alone, we can attach a sieve with only two holes to deal with all the possible configurations of x1. And from the rules we have defined earlier, if we fix the size of one hole, we automatically get the size of another. We can still attach a common sieve to the couple x1, x2, but the sizes here are governed by the size of individual sieves. Doing the same as before, we consider the parameters in the probability distribution as coordinates in 3D space. Now we can go back to the tetrahedron and look at the implications of the independence assumption. Out of all the possible joint distributions, only the ones shown in orange can be a possibility if we assume the independence of x1 and x2. Sometimes the variables in question are actually independent, and sometimes we assume their independence, but that is out of scope of this video. The thing I want you to take away from this video is an intuition of what happens when the independence is assumed, which hopefully was made a little clearer.